Let's see. Hello. Um, okay, you should see the desktop now. Um, can you hear me? Is everything seem okay?
Yes, sir.
Okay, great. Let me pop up Windows. Okay, so okay. Now let's see. Where are we? Uh, Remind you that there's a homework assignment due. The homework assignment's due Thursday. Okay, so the homework assignment's due on Thursday, and then the week after that there'll be this little take-home test. Okay, and the review problems are here. Okay, so there's review problems. Okay, and the exam is on renders up through this one here that we'll talk about today. Okay, so these are the last two renders. There's two more ideas that we're going to talk about that are both applications of this Lerp formula. So we're going to talk about anti-aliasing and then color. Okay, so that's what we'll be talking about this week. I don't know if we'll get this all this today, but we'll be talking about this week. Okay, so first, anybody got any question about where we stand at this point? Any questions at all? Any, especially about the homework? Is anything funny about the homework that anybody wanted to ask about? Anything? If you have questions, send me an email or come to office hours or arrange a talk. Okay, so if questions come up when you're looking at the homework assignment, or if you're looking at these review problems, if you have questions about the review problems, that's definitely ask about those. If you want to talk with other people in the class about the review problems, that's a good idea too. They are review problems. So I always say that you can work together on review problems. You can talk with each other about review problems. That I hope that they are good places for you to talk about the material as a good way to make sure you understand all the ideas in the material. So ask questions about review problems, talk about the review problems with other people. Okay. Let's see. Now, let me just download all these zip files. Okay. What we're gonna do now is I think we've said everything we want to say about clipping. The single most important idea in clipping is this Lerp formula, which we're going to keep using a couple more times. Okay. I got these all unzipped now. Okay. Now, um, one thing. I think it's in here. Oh, well, yeah, I don't think there's anything more I want to say about. I think we covered everything about clipping. So I did rewrite the clipping stage. Remember at the end of last meeting, we were talking about the clipping stage being kind of hard to read, and I did rewrite it. You probably don't remember what it looked like, but what happened was this step 3 was huge. Okay, this step 3, because you have to clip on either the top. You're going to clip on one of these 4 lines. So you're going to clip on one of these 4 lines. So when it came time to decide that you weren't trivially accepting and you weren't trivially rejecting, then you had to clip on one of 4 lines. So this step 3, for the step 1 was trivial accept, this was trivial delete. Step 3 was which line are we clipping on? And instead of doing a bunch of messy code that said which line are we clipping on, I just said you recursively clip on the interpolated line. So I thought that was more declarative. So what you do now is when you get to the clipping stage, you recursively clip the new clipped line. And this method now gives you a new line that is the clipped line. So I thought that read more better. So the algorithm is to clip this line, which gives you clip this line, which gives you that, and then recursively clip that new line. So you clip this line, then recursively clip the line. Because remember, we saw in examples that a line can need to be clipped several times. It was in this other example. Yeah, a line might need to be clipped once, twice, 3. Yeah, it might need to be clipped a bunch of times. So after you clip off one piece, you recursively clip what's left. Okay, well, that's what the algorithm says now. The algorithm says in step 3, recursively clip the clipped line. Okay, so but then that moved all the messiness down into this one method. Now this one method is messy. But this is all the code for clipping is now isolated into one method. Instead of being sprawled over a couple methods, it's all in one method now. So, and there's still, this is the part that I was not liking so much. There's still this kind of stuff. See, there's 8 of these blocks that all look alike. Yeah, so there's 8 blocks, 1, 2, 3, 4, 5, 6, 7, 8 blocks look alike because there's 4 line segments. The 8 cases are 4 line segments, 4 line segments, but then you could have either V1 on the outside or you could have V0 on the outside, which are actually separate cases. So you have a line like this, but you're moving from here you're moving from inside outside, and in the other case you're moving from outside inside. So those actually had to be treated as separate cases. Is V0 is on the inside or V0 is on the outside. So you get these messy 8 cases, which I still trying to figure out if I can make this part look better. But look, that's a big block of 8 repetitions. But they're not quite repetitive. The block is 4 lines long, and the 4 lines differ a lot. They differ quite a bit from one to the other. So if I turn this into like a method, it's just going to be a method with 6 parameters, and it's just going to be 6 messy method calls. Yeah, and it may not end up being any more readable to have 8 messy method calls, with each method call being a bunch of parameters, or just have that repetition of lines, that repetition of lines. Okay, so there's that block, and then the rest of the algorithm is real straightforward. It's actually not that many more lines of code. Okay, so I did rewrite it to make it to make it a little bit better looking. And that's the last thing we talked about the other day, was how the code was kind of unavoidably repetitious. And unless I come up with a really clever idea, I think I'm stuck with the repetitiousness. Sometimes you just can't avoid repetition. Okay? All right. Oh, and if you do this extreme clipping example, this one lets you watch the algorithm. So let's look at this one real quick. The clipping algorithm clips on this line, then recurses. Then the clipped line is clipped on this line, and then it recurses. Then the third line is this one, and then the fourth line is this one. So this line segment will get clipped all 4 times, because on the first pass through, it'll get clipped on this line, and it'll take off this little piece. Then the second time through, it'll get clipped on this line, which will take off this little piece. But it still isn't ready for a trivial accept or trivial reject, because it's still got this part here and this part there. So the third time through, it'll be clipped on this line, which will take off that little piece. Then the fourth time through, it'll be clipped on this line, which will take off that little piece. Then finally, you're left with the part between V4 and V5. So V5 won't be, the first time through, you'll get V2. The second time through, you'll create V3. The third time through, you'll create V4. And then the fourth time through, create V5. And then finally, the line from V4 to V5 is trivially accepted. So it takes all these trips through the algorithm to get that line clipped. That's the extreme example. Okay. What's a little bit interesting is these vertices are left in the model. All these vertices are left in the model. You might think you remove them when it's clear you don't need them anymore, but there's it's either you can't remove them or it's not worth the effort to remove them. For example, you can't remove that line from the model. And that's shown in the README, at the bottom of the README. Here's a line segment where you need to clip off this guy. After you clipped off this guy, you can't throw him away because he's also the line end of that line segment. So if you threw that vertex away after you clipped it off, if you thought that, oh, after you clip something off, you could throw it away, that might be a mistake because there could be another line emanating out of that vertex. There could be a whole bunch of lines emanating out of that vertex. So here, there's two lines emanating out of that vertex. When you're clipping this line, you're going to replace that vertex with a vertex over here. And you got to be careful. If you throw that vertex away, then this line gets clipped wrong. See, like if you actually move that vertex over to here, you make a mistake because that makes this line segment go like this. So you got to leave that vertex there. You got to leave that vertex there and create this new vertex. Okay. Then when this line segment gets clipped, again, you can't necessarily throw this guy away because maybe there's still a third line using it. So, and it would be too much work to determine when that vertex is no longer in use. You could do like a little, you'd have to write a little mini garbage collector in the renderer to determine when a vertex in the model is no longer in use. That's exactly what a garbage collector does in the heap. Here we would have to say, oh, I've got this vertex in the model and no line segments using it anymore. But garbage, who wants to write a garbage collector? And it would be a waste of time. The key idea is it would be a waste of time because renders need to be as fast as possible. So you would not bother to write a garbage collector to say, oh, look, I've got a vertex that's no longer in any line segment. It would literally be writing a garbage collector for the model. Okay, so now this one, you could make a case, oh, you should get rid of it when you clip off to here, because this one's not going to be shared by anybody because it was put there when you clip this one. But again, it's just not worth the effort. When you clip off this one and you replace it with this one, okay, at that point you can say, what, and then this one's going to get clipped off to be replaced by this one. You could say, well, this one was just put in there a second ago, so let's remove it. We don't need it anymore. It's just not worth the effort. So when we run this program, we'll see all these vertices get left in the model. So let's go ahead and compile it and run it. And this is one of the beauties of having a software render. In an OpenGL graphics render, you can't ask the graphics card to show you what it's doing. There's no way to ask the graphics card to show you everything it did. Okay, but here we can ask the renderer to dump information. So this program, this extreme clipping example, turns on the debugging in the renderer. See, it turns on the debugging. It prints the model out before rendering it. It has debugging turned on, so you get all this output. Okay, so here's the information about the model. It's a real simple model. It has these two vertices and one line segment. Okay, so that's the dump of the model. It has two vertices, one line segment. Vertex index 0, vertex index 1, line segment from 0 to 1. Okay, now start rendering it. Okay, I put those vertices in the projection plane, so they're not going to get projected. So just because this is a simple example, the vertices are already in the projection plane. So here they are in camera coordinates. They just get projected to themselves. So that's not what we're interested in. We're interested in clipping. Okay. So now you're going to clip the line segment from vertex 0 to vertex 1. Okay, and you're going to clip off vertex 0. Okay, vertex 0 needs to be clipped off. So we're going to clip off vertex 0 at line x plus 1. Okay, so see, the render is telling you exactly what it's doing. It's designed to show you step by step what's going on over here. And when you're solving some of the problems on the exam review, this is what I'm asking you to do, is like look at the output from the renderer to explain to solve the problem. It helps solve the problem by looking at what the renderer does. Okay, so here you're going to clip off v0 at x plus 1. Okay, so then this is the new point. This is the point that got clipped. Okay, notice that it got clipped with x equal 1. So the new vertex has x equal 1. So when you clip off this one, the new vertex should have x equal 1. Now the y-coordinate, who knows what it is? See, the y-coordinate got changed from negative 1.5 to, let's see. Oh, no, there's the inside one. It's the outside one. We're clipping off. No, let's see. Yeah. Oh, this is inside outside. Okay. In this line segment, the one we were clipping off was the outside. This one is the outside one. So V0 is the one being clipped off. So 1.25, 1.5 is being clipped off. So this is 1.25, 1.5 being clipped off. And we're clipping on the x coordinate. So see, there's the clip where the mouse is. 1.25 got clipped to 1.0. And the y-coordinate got slid over a little bit. So the y-coordinate got slid down, and the x-coordinate got cut off at 1. See, so when we chopped off this one to this one, y dropped, x got cut off at 1. So y changed from 1.5 to 1.2, and x changed from 1.25 to 1. And here's something really interesting to show you how crazy this stuff is. Look at that guy there. What is that? How would you tell it? What is that?
Does that have to do with the Java adding on that like little when it rounds, a rounding error?
Well, what do you mean? What is that thing? Where'd that 2 in the 17th decimal place come from? If you do the arithmetic, the answer should be 1.2. Right? If you go and do the arithmetic on this point, you'll see that the answer should be 1.2. So the answer should be, the y-coordinate should be 1.2. What is this guy here? What's the word for it? You used it. It's what?
Was it rounding error?
It's actually something like a rounding error. Okay, and it's got nothing to do with Java. What's it got to do with?
Oh, maybe what's in the memory locations?
No.
Oops.
Yeah, it's not a Java issue. It's a what issue? Binary. But binary what? Binary what? It's a binary issue, but even more specifically, binary what's? You'd have this problem in C++. The exact same thing would show up in Python. It wouldn't matter what language you're using. We'd get exactly this number, 1.200000002, because we're using what? Binary
encoding.
Pardon me? Binary encoding of what? Binary encodings of
Floating point?
floating point numbers. This is an issue with the floating point number system. The floating point number system doesn't translate decimal numbers into binary numbers completely accurately. It's an effect of the floating point number system. Okay? Right? So, for example, how many times should this line get clipped? This line should be clipped what? Once?
4 times.
4 times. Look over here. It got clipped 1, 2, 3, 4, 5 times. We're going to see in a minute. It got clipped 5 times. Anybody want to guess why there was a 5th clipping time?
That 2 you're talking about?
It caused one of the points after it got clipped to actually be still on the wrong side of the clipping line and had to get clipped again. This is an endlessly complicated problem for real graphics renderers. One of those, when we did one of these clippings, I think it's the last one, when that point got clipped, that V5, after it got clipped, it rounded to the wrong side of the clipping line and then had to get clipped again. So it had to get a fifth clipping. So let's step through and we'll see that that's going to happen. So that another another two like that's going to show up later on, and we'll see that it causes us, it actually, this time it didn't cause any grief. The 2 is in the y coordinate. We clipped the x coordinate. That extra 2 is in the y coordinate, which we don't care about. Okay, but watch as we keep going. Okay, now we've got this. Now we know that the line is over to here. Okay, now the second time through the clipping algorithm, we're going to clip from V2 to V1 on -1. Okay, so we're going to clip from V2 to V1, except that V2 will be one of these. This is going to be V0 now because this one will be called V0 in the renderer, because the line segment will go from here to here. Okay, so now we're going to clip off V1 at x equals -1. So we're going to clip off V1 x equals -1. Okay, and it's going to clip to -1, -1.2. Notice that this time we didn't get any funny number down here. Okay, we didn't get a funny number down here, even though we were clipping the same number. But notice what's different. How come this one clipped differently than this one? Even though the numbers, see, it started off 1.25, 1.5. Okay, what's different here than here that would make you think, okay, there's a reason why this one could be different than this one.
Maybe because it's negative, it's the reverse effect.
Yeah. Sometimes you round in different directions. See, if you're rounding down, on the positive side, that rounds to 0. On the negative side, that rounds away from 0. If you're rounding up, on the positive side, that rounds away from 0, but rounding up on the negative side rounds towards 0. So depending on whether they're rounding up or rounding down, you can get different things on the positive side of the number line and the negative side of the number line. So we got on the positive side of the number line, we got this little guy, and he didn't show up on the negative side of the number. Even though the numbers are all the same, this is actually the right thing. But so what happened was there was some kind of little rounding up. And over here, the rounding up it rounded in the right direction from our point of view. So we got the right answer. Okay. All right. So now we've got the x coordinate at -1. So we clipped there. Okay. Now we got to clip again. Okay. Now we know that the next one's going to be at y1. Let's see. Yeah, at y1. So now we're going to clip off V0 at y+1. Now notice it says V0. It's really this guy here. This guy is now V0 because he replaced V2. What we're calling V2 in this picture replaced V0 in the line segment. So the renderer says we're clipping off V0 at y+1. And that's this guy here, 1.20, 1.2000. And you can see him. He's on the outside. See, there he is. See that 2 there? That's him. See, he's on the outside now. See, he is the outside on this line here. Okay, now he's going to get clipped off. Y is going to drop and X is going to move over. And he's going to clip off. Y is going to drop. Oh, look, it dropped to just where it should. It really is at 1. And X moved over. Okay, so X moved over and Y dropped to 1. Okay, so that was clipping on Y1. Okay, now we know the last one's going to clip down here. The fourth clipping is we're going to clip off V5. Now V5 now is really V1 because V3 replace. Well, I'm sorry, we're going to clip off V3 and create V5. But V3 is really V1 in this, from the renderer's point of view, because when we clip this guy off here, he became the V1 on the line segment. Okay, so we're down here. We're going to clip off V1 on y equals -1. So on this line segment, we're clipping off. It's really that guy there. Okay, all right. So we do the clipping. Okay, and we're going to clip off the y coordinate. We're clipping off the y coordinate to -1. And now look, the y coordinate was -1.2, 0, 0, 0, and he clipped to -1 with a 2 here. But that 2 pushes us down. We're actually rounding to the wrong side of the line we just clipped on. We clipped on that line, then the rounding put us back on the wrong side of that line. So then we need one more clipping stage. Now, on the next clipping stage, look at the T. the t is almost 0. So, because what we're doing now is we're clipping a line that's just a tiny, tiny gazillionth of a pixel over that line. Okay, it's literally a gazillionth of a pixel. Because look, how many? It's the t value is 0, 0, 0, 0. There's like 15 zeros there before we get a 1. So we're talking about, you know, clipping a line. We're clipping a point that's that far away. That's a lot of zeros. You know, that's a lot of zeros. We're talking a quadrillion, you know, less than a trillionth. Because how many threes?
A pico.
Pardon me?
A pico.
It's probably even smaller than a pico. Because how many? I mean, it looks like there's about 15 or 16 zeros there. A pico, isn't pico 12, 15 zeros?
Yeah, I think pico's 15.
And that's about where we are. It might even be more than 15 zeros. Okay. Yeah, I can't count them. Okay. So, but you know, so then we get a t that, you know, but notice that we have a fifth clipping. This actually causes, there is massive amounts of research into this. This causes real grief in some algorithms, because here, you know, we naively thought we should clip 4 times, but we actually needed a fifth clipping. Depending on what you're trying to do, depending on the algorithm you're writing, these little rounding errors can really cause grief. There's a branch of computer science called algorithmic geometry, and they're the ones who try to do real they compute with points. Algorithmic geometry, or people they call it computational geometry. They compute with points. It becomes an important part of image processing. Did I spell it right? Oh, computational geometry. Computational geometry is notoriously difficult to do because of rounding errors. And there's a huge amount of research in this field because they take these huge numbers of points and they try to do algorithms on these numbers of points. It's real important in CAD in numerical analysis. It becomes important in numerical analysis for solving differential equations. But their algorithms get really messed up by these kinds of little mistakes. So they've written all kinds, these people in particular, the computational geometry people, have actually done an amazing amount of research in numerical and floating point numbers. I think the best literature on the nature of floating point numbers is from their research, because these rounding errors cause them so much trouble. And we see it here. Our algorithm did a step we didn't expect it to do. Our algorithm did a fifth clipping step because of that little 0.2 there. Okay, and you get this weird number here. Oh, at one point I had a bug in my algorithm. Okay, here's an example of how this can cause real grief. Okay, suppose you clip that line this time, and suppose after you clip him, he rounds to the wrong side again. And then you clip him, and then he rounds to the wrong side again. What happens?
Does it start growing?
No. Think of it. You clip him, round, you're on the wrong side. Clip him, round, you're on the wrong side. Oh, sorry, endless loop. Yes, and that's happened to me. I've actually had my render fall into an infinite loop because of this rounding error. That's the kind of grief that they can get in, these computational geometry people can get. It's actually happened. And here's how I fix that infinite loop. See that commented line there?
Yep.
See, what does it do? Right now it's commented, but I can put it back in anytime I feel like it needs to be there. What do you think what does that line of code do?
To make a threshold?
No, think of it.
Keep the vertex off.
Okay.
Oh.
Adds an offset greater than the rounding error.
Yes,
Yeah.
so it does what in the algorithm? After I clip that point, what does it do then?
It will ignore anything less than?
No.
Okay.
See, I'm solving for the t. Remember, the t is, okay, remember the algorithm is that you're traveling from here to here. At time 0, you're here. At time 1, you're here. So you're traveling from here to here. Then you find the time when you cross that point. Actually, the traveling is from here to here. And you find the when you cross that point. Then when you know when you cross that point, you find out where you cross that point. So the algorithm is to first find out when you cross, then to find out where you crossed. Why does this fix the rounding error?
It moves it just beyond where it crossed.
Yes, it advances time by a tiny amount. So it takes that point there and pushes it forward in time along the line a tiny amount. So it pushes it inside of the clipping region, off of the clipping line. It just arbitrarily bumps it forward in time a tiny amount. Now I just picked an arbitrary tiny amount, and it moves it forward in time. Now that actually, from the computational geometry people, that's not a good thing to do because I'm moving the point. I'm supposed to be computing this point, and I'm just arbitrarily bumping it. Now in my case, it's a bump. I don't care. It solves my problem. It doesn't really, it just pushes this line off. It pushes this point off the line a tiny bit, enough to make sure that it's not still on the wrong side. So you can see that now I'm assuming that the problem here is always more than that many decimal places away from the origin. So I'm assuming that the problem is never over here. I'm assuming the problem is always over here. And I think that's a safe bet. I'm assuming that's enough zeros that the problem is always going to be to the right of that in the number. So I can just push my way off of this. I can just push my way off of this line a tiny bit. Okay. It was a bizarre coincidence when I made this example that I hit upon an example with this rounding error. These rounding errors are actually hard to cook up because you don't know. Floating point numbers are really weird. So when I wrote this example and then I ran it and I thought, oh, wonderful. Yeah, by some bizarre stroke of luck, I actually landed on a rounding error because the rounding errors are almost kind of randomly distributed through the floating point number system. Some floating point numbers round, they round in really kind of complicated ways. So I just got lucky that I hit on one. So I created this example, and just the numbers I chose at the beginning just happened, even though, look at the numbers I chose, 1 1/4, 1 1/2. Those are very normal numbers, 1 1/4, 1 1/2. But those numbers led to rounding errors. Bizarre little rounding errors, even though I'm using really what you think of as very normal numbers, 1.25, 1.5. That shows you that even common numbers in our decimal number system can have troubles in the floating point number system. Okay, so even common numbers can cause you grief in the floating point number system. Now here's what I wanted to show you is that after all that clipping, now I only have one line segment. It's only using 2 vertices, but all the previous vertices are still in the model. The model does not get rid of V0, V2, V1, or V3. It keeps all those vertices, and actually keeps even the extra one that we didn't need. Okay, and so it ends up going from a V4 to a V6. See, the actual final line segments from V4 to V6. See down here? From V4 to V6. The 4th line and the 4th vertex and the 6th vertex, because the 5th vertex got clipped a second time. So notice the difference between V5 and V6. Notice that, well, they look the same. Why are V5 and V6 not really the same? See, look, V5 is, pardon me?
The decimal place
Yeah,
doesn't
here, to make it easier to read, I only showed 5 decimal places here. The V5 and V6 differ way out here in like the 10th decimal, the 15th decimal place. So when you display, this is another problem with floating point numbers. Sometimes you got to look at, that's why here I'm displaying all of the decimal places. Because if I don't display all of the decimal places, you don't see what's really going on. Down here, I'm summarizing things, so I only show 5 decimal places, which is just a summary. So these two, V5 and V6, look like they're the same number, but they're not. They really, if you extend them out, you can see over here, here's V5 and V6, you can see that they differ. Well, look, V6 actually is 0.999999999, so it's rounded to -1. But it's really, look, 0.9999999 with a bunch of zeros at the end. And so it rounds to -1. Okay. Floating point numbers are inherently hard. And renderers have to deal with them a lot. And the clipping algorithm is notorious for being one of the places where in the render you can get bitten by a floating point error. You know, the clipping algorithm is one of the places where it can actually really, you can get a bug in your clipping algorithm. Like I said, I actually had once I came up with an example where my render actually got thrown in an infinite loop because that every time it clipped that thing off, it would then round to the wrong side of the clipping line. They would clip it off again, and it would round right back to the wrong side of the clipping line. And I should have saved. I was dumb enough to just fix the bug and go on, and I should have saved that bug because that would have been a great example to remember. But I probably will never see that bug again. Okay, but here by luck it showed up as a simple example where it just gets clipped one extra time. It didn't clip. No, when it got clipped the second time, it stayed where it belonged. The second time it clipped, it didn't. Actually, it clipped to be slightly on the right side. You know, it clipped to be just a little bit. It actually clipped a little bit to this side of the line. You know, it actually clipped a little bit on the wrong side of well, from our point of view, it clipped to a little bit on the right side of the line. So you see how delicate this is going to be. Here it clipped to the wrong side of the line. By good luck, this time it clipped to the right side. It didn't clip on the line. It clipped off of the line, but on the side we wanted. If this one had clipped on the wrong side again, we could have potentially ended up in an infinite loop. Yeah, we clipped on the wrong side, then we clipped on the right side, and we potentially could have had an infinite loop there. The clipping algorithm doesn't try to clean up. It does not go in and say, oh, this vertex no longer being used, this vertex no longer being used, this vertex no longer being used. That would just be a silly waste of CPU cycles to do a garbage collection on the vertex list, because and I'm sure the GPU doesn't bother to do. The GPU is going to have to do the same thing we're doing here. The GPU has to, when it clips lines, it has to keep the old vertices because those old vertices might be part of more than one line. So as we saw, in this picture here, you cannot just throw away. You don't throw away a vertex after you clip on it, because the vertex could be part of another line. So the GPU is going to be doing the same thing, but I don't know if I don't know where to find the documentation of how the GPUs actually solve these problems. It's very hard to find out what's really going on inside of a GPU, mostly because I think a lot of it's proprietary. The algorithms they use are their bread and butter. So they're not going to tell their competitors, oh, we got this great fast algorithm for line clipping, unless the algorithm is done in the research literature from a university somewhere. But it's very possible that people like NVIDIA.
Professor Kraft?
Yeah.
When you do the t plus equals and add that little bit to it, does it create a new point or does it keep the old one?
This is just before it creates the point. So then here's when, see, I do this bump. Here's where it creates the new point. So I do the bump just before it creates the new point.
Okay, so it keeps the old one.
Well, the render, no.
No.
Here, okay, here's the old one.
Well,
it's going to be clipped to here.
Right.
The algorithm first computes the t. Then before I compute this vertex, I bump t. Then I compute the vertex.
Oh, okay.
So I never compute the wrong vertex or the one on the wrong side. What I do is I compute the t here, then bump it, then compute the new vertex. See, use the value of t to interpolate the new vertex. See, so compute the t, bump it, then compute the new vertex.
Okay.
So I don't create, so I bump the t before, so I don't, for all I know, the t is okay, but I just go ahead and bump it anyway. Now, that's why I had this commented out. As long as it's not causing me any grief, right now I'm kind of experimenting to see if I ever get that infinite loop again. So right now I've got that t commented out, kind of hoping that I hit on that infinite loop again someday. Now, I don't know if renders, like, do GPUs, do they bump their T like I'm doing here? Or do they have much better numerical analysis? Do they use better algorithms? I don't know what they do. I don't know if they have either a better numerical algorithm so they never get the rounding the wrong way, or if they just do kind of like what I'm doing here. After you get the T, after you compute the correct T, but it might be rounded wrong, just bump it. You know, I just arbitrarily bump it. So that bumps you, that just arbitrarily bumps you back inside. Yeah, if you're slightly over the line, it bumps you probably on the other side of the line. And if you're right on the line where you belong, it just bumps you inside of the clipping region anyway. But it would be an imperceptible amount from the visual point of view. That's the distance I'm bumping is way less than the size of a pixel. That's way less than the size of a pixel. So I'm not going to see that bump. So it's from that point of view, from my point of view, it's not a big deal if I bump it. From the computational geometry people, it can cause them real grief to bump these things, because their algorithms need to be very precise when they with what they're doing. Okay. All right. So that's kind of interesting that I can see numerical rounding errors real quick. Just simple examples can lead me to see floating point errors. And these are unavoidable errors in the floating point system. You work with numbers as simple as 1.5 and 1.25, and you do a little bit of arithmetic with them, and you get weird answers right away. Okay, weird answers, just simple arithmetic. Okay. All right.
I have a question.
Yeah.
If you know that you want to clip to y equals -1 and it's slightly, the computed value is slightly above or below, couldn't you just like use a floor or a ceiling to get to y equals -1?
Yeah. Let's see. Now that would have to be, see, then that would add another, that would be in each, let's see. Like here we're clipping to x equals 1. Yeah, I could do that, but see sometimes you're clipping to x equals 1, sometimes you're clicking to x equals -1. So then down here, I would need a bunch more if statements. See, here I compute x and I compute y, right? Using the t. And you're right, I could just say, if I'm clipping on x equals 1, then this x should be 1, not this computed value. If I'm clipping on x equals -1, x is -1, not this computed value. If I'm clipping on y equals 1, y is 1, not this computed value. If I'm clipping on -1, y is -1, not this computed value. So you're right, that would be kind of, yeah, what would be the disadvantage of doing that? Then I would never have this rounding error, but what would be the disadvantage? It's a real good point, but what would be the disadvantage?
Take more time? Or?
Yes, I'd have more if statements. Now, what's wrong with if statements? If statements are particularly bad. For one thing, it takes time to compute the if. You have to compute if I'm checking x equals 1. But what's the real problem with if statements?
They jump to a different location?
Yeah, so what's wrong with that? Very low level. We're computer scientists. We simultaneously think from atoms to algorithms all at the same time. We're always going atoms to algorithms all the time.
Memory mapping and
no, close. What's the issue? An if statement jumps around. What's wrong with jumping around?
If what's it called? Virtual.
No,
I can't think of. Sorry.
Yeah. No, it's not virtual. It's not the virtual. I mean, if you think of virtual memory, it's not an issue with cache lines or anything like that.
Yeah, that's where I was going with
No,
that.
it was. Yeah, it wouldn't be a cache line problem. But it is a CPU problem. Jumping around causes what in the CPU?
Inefficiency?
Yeah, but does anybody remember what's the inefficiency it causes? It's got an actual, it's a real specific issue. It causes what's called a branch prediction stall. Because of the CPUs are what we call pipelined, it causes a pipeline stall because the CPU is always trying to guess what the branches are going to do. And whenever you have branches, every time it misguesses the branch, it slows the CPU down a little bit. So if statements cause branch prediction failures, which slow the CPU down. Okay. Okay. So that's it's a very subtle issue. But when you're trying to speed up code as much as possible, like in a GPU, you actually do worry about those kinds of things. If statements, every if statement is a potential place where your CPU can have a pipeline stall, what's called a pipeline stall. Okay, so if statements, so you're right. That would fix this problem entirely with a bunch of more if statements down here that said that, if I'm clipping on x equals -1, then x should be -1. If I'm clipping on y equals 1, then y should be 1. And that would fix the rounding problem at the expense of a few more if statements. Okay. But then, then I would have to go down here and do these if statements all over again. Or I could move these two lines of code into every one of these blocks. Actually, yeah, that I could take this two lines of code, for example, and move it there. Okay. Now, what would I say? I'm clipping on x equals 1, so 1. But compute y. Right? And then here, I would say, same thing. Well, I'd have to make sure I'm using the right formula. Yeah. Yeah. So then I would just essentially have to do the same thing here. Yeah. So I would, that would actually have an advantage of not introducing any more if statements, because I'm just folding this code inside of these if statements. Okay, so see that, and then compute y. So in this case, x's are 1, and then compute y. But then over here, you would have x is -1 and compute y. Okay, same here. Okay, but then here, now you're on y equals 1. So now the code would look different. Now you'd have to go. Now you would interpolate the x. But now the y would be, let's see, we're doing y equals, so now you say, oh, the y is 1. Okay, so I could do it that way. It would just be putting more code in these blocks, which makes them just messier looking. But actually, that might actually be possibly the most efficient way to do it, because I wouldn't be introducing any new if statements, because I would just put that code right in these blocks. So since I already had to jump to this block anyway, that would put the code in the block, and then these guys would never be rounded wrong, and these guys would be the right value. Okay? And then you'd get down here, and you wouldn't need those two lines of code anymore. Okay, so just kind of fold those up into there. That would probably be, that might be what the GPUs are, because if you didn't care about anybody reading your code and you just wanted the solution that was the most efficient, maybe this might be okay. Yeah, because it makes the code a little bit messier looking, but it does solve the problem of the rounding error. You'd never get the rounding problem because of that. See, the rounding would be gone because of that. Okay, all right. So that would be a potentially nice way to solve the problem. Okay, now let's go and let's okay. So that's everything about clipping. So we did this is the last example to look at in clipping. So let's go ahead and start talking about anti-aliasing. Okay. All right. So let's see. Okay, what is anti-aliasing? Let me oh, I know it. I want the little tools for magnifying pixels. I want to go back to the website. Remember, we have those tools for magnifying pixels. So from earlier in the semester, we had these little pixel utilities. Let me down those. To see what anti-aliasing is, I want to be able to examine pixels again. Let's see, I think. Okay, now let me run a code example. Okay, this is what those lines look like. See, they're very jagged. So, yeah, those lines have what we call jaggedness. Okay, the idea of anti-aliasing is to smooth out the jagged lines. Okay, now one thing that's interesting in what we're talking about now is anti-aliasing is quickly becoming not important. It used to be one of the a really important part of computer graphics, and it's no longer all that important because monitors keep getting higher and higher resolutions, and you don't see the jaggedness anymore. You don't, if you ran this program on a 10 or 15-year-old monitor, you'd actually kind of notice that some of these lines are jumpy, like these lines down here at the bottom. You start really noticing that they're jumpy. You start seeing these, I'm trying to find a jump. You start seeing those things. But on a modern monitor, the pixels are so tiny, you don't see them anymore. Now, if I click on this picture on the right, it's smooth. It did what's called anti-aliasing. Notice that on the left, see how pixels now are shaded? What we're doing is, see, this is aliased. This is anti-aliased. What I'm doing is I'm averaging the pixels to create kind of a blurring effect. Now, on the right-hand side, you might notice that the lines become a tiny, tiny, tiny bit smoother when I turn on anti-aliasing. See, now anti-aliasing is off. Now anti-aliasing is on. The screen's not updating. I have to move the mouse for the screen to update a little bit. It shouldn't be that way. The screen should update automatically. I'm not sure. Oh, it's the zooming tool that's not updating. Yeah, the zooming tool is not updating itself unless I move the mouse. So when the screen that's a bug in the zooming tool. When the screen updates, the zooming tool doesn't update itself. If you look on the right, I'm turning anti-aliasing off and on. 10 years ago, you'd see a big difference on the right. But now you barely see any difference at all. And in another 10 years, the pixels on the screen are going to be so tiny that no one's going to be worried about anti-aliasing anymore. Okay, so the idea is that when you have these jagged lines like this, if you blur them by averaging pixels across two pixels across the line, you make the line look a little bit smoother. Okay, so here's what that looks like in an explanation. Okay, look at this readme about anti-aliasing. Okay. Here's the pixel plane. Here's a line going through the pixel plane. The dots are logical pixels, the points that have integer coordinates. The squares are physical pixels, what gets turned off and on the monitor screen. Okay, so in this line, you would turn on these pixels, this pixel, this pixel, this pixel, because those are the pixels the line is closest to. Obviously, that pixel there would be turned on. Yeah, if you see this line here is between that pixel and that pixel. It's closer to this pixel, so that's the pixel we turn on. Now over here, that line is between that pixel and this pixel, but it's obviously closer to the left-hand one, so we turn on this pixel. So you can see the line is closer to this pixel than it is to that pixel. Now in this row, the line is between that pixel and that pixel, but it's closer to that pixel, so we turn it on. Now notice when I use the word pixel, I should say it this way. This line is closer to this logical pixel than it is to that logical pixel, so I turn on this physical pixel. I turn on the physical pixel that belongs to the logical pixel that's closest to the line. And again here, the line is between that logical pixel and that logical pixel, but it's closer to this logical pixel, so I turn on that physical pixel. All right, that's alias lines. Now, what do I want to do if I want to anti-alias? To anti-alias, I say, well, like, look at this example here. It's almost exactly halfway. See, this is halfway between the two logical pixels, right? That edge is halfway between that logical pixel and that logical pixel. This line is almost halfway. So why not turn on both pixels? So turn on both pixels, but at half the brightness. Okay? The idea would be you turn on both pixels at half the brightness so that it's the same amount of light coming out, but half the light comes from this pixel and half the light comes from this pixel. And even in this one, I should show you, like, this is the line is 90% of the way to this pixel. So you would actually maybe turn on this pixel at 90% and turn on this pixel at 10%. To account, see, what we're going to do is we're going to linearly interpolate between the two pixels. So this is where the lerp comes back in. What we're going to do is we're going to turn on two pixels. See, the line is between that pixel and that pixel. Well, where is it? Is it halfway between them? 3/4 of the way between them? So then the intensity of this pixel and the intensity of this pixel would be the lerp from, you essentially say, as you move from here to here, as you get closer to, as the line gets closer and closer to there, this pixel gets brighter and this pixel gets dimmer. So if you think of yourself as moving, remember the Lerp formula was the idea that you move from one place to another place. With time t equals 0, you're here. At time t equals 1, you're here. Okay. At time, you compute the time when you hit the line. Okay. And then you use that time as the weight for the pixels. This pixel is weighted inversely proportional to time. The farther away you are from here, the dimmer this pixel is. This pixel is directly proportional to time. The more, if I'm measuring time going from this way to this way, then this one would get, as time increases, this one gets more weight. On the other hand, I could measure time going this way. If I wanted to, I could measure time going time 0 here, time 1 here, and then if I'm close to this time, this one gets more weight and this one gets less weight. Okay, so here's the Lerp formula. See, I'm going to use the Lerp formula. So here's the picture of one row of pixels. I'm going to lerp from this pixel to that pixel. I'm going to lerp from P0 from pixel 0 to pixel 1. At time 0, I'm at pixel 0. So you can see when time t equals 0, 1 minus 0 is 1. 0 times P1 is 0. So at time 0, I'm at this pixel here. So at time 0, I'm at that logical pixel. At time 1, 1 minus 1 is 0. So this is gone. At time 1, I'm at P1. So I'm going to move from P0 to P1. At time 0, I'm at time 0, I'm at P0. At time 1, I'm at time 1. and I want to solve for when do I cross this line? When does my line segment cross that line? Okay, so when does the line segment cross that boundary between the two pixels? Then I know, once I have the when, I use the when to give two weights. I give this weight to this pixel. See, think about how that works. I want to know when I hit this line. If I hit it real soon, suppose this line is real close to there, like that would be the example, like this one here. See, oh, I'm sorry, not this line. The when is when you cross this line here. I'm sorry, the when is when you cross that line. I said the wrong, I was thinking of like clipping again. The when is not when you cross this vertical line. The when, as you move across this line, is when do you hit this, yeah. When is that one going to hit there? Okay. So, you know, or another way to put it, as you move across here, when do you hit this line? Actually, that's the best way to put it. The best way to put it is, as you move from that pixel to that pixel, when do you hit that line? Okay. As you move from here to here, at time 0, you're here. You're going to move horizontally. At time 1, you'll be here. And we want to know, when do you hit that line here? Okay. Then when I hit that line, now this one, I hit the line real soon. That's t nearly 0. Okay. Here, I hit the line at about the midpoint. So that's t like 0.6. So as I move from here to here, I hit the line at about, say, 0.6. Here, I hit the line at 0.1, say. Okay. So how much does this pixel get? How much intensity does this pixel get? It gets 1 minus t. If t is real small, this thing is real bright. So if I hit the line real soon, this one's real bright, and this one's real dim, because this one is t. So if I started out from here and hit the line real quick, then this one's bright and this one's dim. On the other hand, if I start here and I have to go real far over before I hit the line, then t is close to 1. So this is dim, the left pixel's dim, and the right pixel's bright. Okay, so I'm asking, as I move from pixel to pixel, from left to right, when do I hit the line? And then the pixel on the left gets that weight, and the pixel on the right gets that weight. As it takes me longer to get to there, that means I have more weight on the right pixel and less weight on the left pixel. The sooner I hit that line, the more weight I put on this pixel, the less weight I put on that pixel. Okay, all right. So that's the Lerp formula for anti-aliasing. Okay, so notice that this is the exact same Lerp formula. If you go back to the clipping, see, that's the Lerp formula for clipping. You want to move from here to here and ask, when did you cross that line? Here's the Lerp formula for anti-aliasing. It's really it's actually almost a completely different thing. Clipping and anti-aliasing don't really look too much alike. I mean, you have lines crossing lines, but anytime you have lines crossing lines, you have potential for lerping. You know, because you travel across a line using the Lerp formula. You travel across a line using the Lerp formula. So the Lerp formula is the way you travel a line. That's in vector calculus, this is called the vector parametric equation of a line. It wasn't called Lerp in calculus. It was called vector parametric equation of the line. Lerp is a lot easier to say than vector parametric equation of a line. Okay, so but it makes you travel along a line. Time 0, you're at one endpoint. At time 1, you're at the other endpoint. Okay. Here, we want to do the same thing. start here, travel horizontally till we get to there, and we want to know when do we cross some other line. Again, here, we want to know as we travel along that line, when do we hit this line? So whenever you have two lines intersecting, there's a potential lerping involved. So whenever, in this case, now that's not the only way you get lerp, but one obvious way you get lerp is you have two lines intersecting and you want to know when they intersect. Here, clipping is, I want to clip that line. I want to clip that line whenever it intersects here. Here, it's not a clipping thing. I want to know how to balance the pixels on the left and right-hand side. I want to balance these two pixels on the left-hand, right-hand side. I don't want to just turn this pixel on full bright and this pixel on full off. I want to say, oh, they should be balanced. The closer I am to this pixel, the brighter this one should be, and the dimmer this one should be. So I want to balance them. So I use the Lerp formula to say, as I move from here to here, when do I cross the line? Solve for t, when. Once I know when I cross the line, then I can say, that's how much weight to put on the left pixel, and that's how much to weight put on the right pixel. Okay, so there's the Lerp formula. And then that's what happens. Go back over here to the picture, to the, do I have the zooming tool? Let me start the zooming tool back up. Okay. You can, what's happened? Oh, see, I can't move the mouse now. Now, here's what it looks like. Let's see, let me find a good. Yeah, if you look, if you think about it, you're going over, let's see, let's find one that goes over a lot of pixels. Like here, you go over 3 pixels, and then you go over 2 pixels, then you go over, oh, let's see, let's get one that goes. Like this looks like you're going over 4 pixels, then 2 pixels, then 4 pixels, then 2 pixels, then 4 pixels, and 2 pixels. Notice that as you go across 4 pixels, you're really rising up through those 4 pixels. On the left, when you see, I'm looking for a run of even more than 4 pixels. Like there's a run of 5 pixels on the left. The line is actually rising up through those pixels. So as it's rising up through those pixels, you should be shifting its intensity up to the row above it. Okay, so where there's a row of 5 pixels in a row horizontally, you really should see it becoming dimmer as you go across the row, and the row above it starting to become bright. Now let me see if I can get it to do that. Okay. No, you know what? I've got the problem. I need to turn off magnification on my desktop because the zoom tool doesn't understand magnification. So if I turn off magnification temporarily, the zoom tool will work better now. Now the zoom tool is exactly where I'm pointing. Before, the zoom tool wasn't exactly where I was pointing. So now, like, I'm down like these lines here. See, these lines here have long runs of pixels. Okay, so here's a line with a medium long run of pixels. Okay, now now let me turn on aliasing. Okay, now see, as I go through the long run of pixels, see, right now the mouse is right over the start of a long run. And see, right where the mouse is, you've got a very bright pixel with a very dim one just above it. Then you move 1 pixel to the right, and the pixel in the row of the mouse is a little bit dimmer, and the pixel above it's a little bit brighter. You move over again, the pixel on the row of the mouse is a little bit dimmer again, the one above it's a little bit brighter. And as you get all the way across that row, you see that the pixel in the row of the mouse has been dimmed down to black almost, while the row above it has been brightened up to white. And then let me go back to where it was without anti-aliasing. See, there it is without anti-aliasing. There it is with anti-aliasing. You can see that as you go across the row of pixels, the pixels get dim. Well, first they get brighter. And if you look at the whole row, they start off black, they brighten up to white, then they go down to black. Okay. When they start off black and going up to white, that's the row that used to be all black. Then when you get to the part where it's white and then it starts dimming to black, that's where it used to be all white. Okay. So here now you have it going from, I can't move the mouse. I wish I had a second mouse, because if I move the mouse, then I'm moving it in the picture on the right-hand side. Okay. But where you have a row of white pixels, now as you move to the right across that row of white pixels, you're going to be shifting weight up. As you move across to the right, because as you move across to the right, those pixels should be becoming dimmer. Okay, because the line is moving up through them. The line is actually, if you imagine the line itself, the line is crossing from the lower left-hand corner of one of these white stripes to the upper right-hand corner of that white stripe. It's moving up through the stripe. Okay. There's pictures that kind of show this in the fold. Like if we go to the folder on rendering, the one that has pictures. Okay. Here's some pictures that kind of demonstrate the idea. You'd like to draw a line like this, but pixels can't go diagonally. There's no such thing as diagonal pixels. So to get diagonal, this is a really nice picture of it. This is kind of a nice way to show it. You really wish a line went up like this, but pixels aren't diagonally shaped. Pixels are horizontally. So what you wanted has to be turned into a row of pixels horizontally, a row of pixels horizontally, a row of pixels horizontally. Okay, so that's kind of a nice way to think about it. Okay, so you're stuck with this when you really wish you had that. And no monitor can draw that. No monitor can draw that. Okay, then here's the idea. We're going to take these pixels and blur them. And you can kind of see, like this line here, see how it got blurred. These pixels that were black all across became steadily getting lighter and became lighter, while the white pixels above them became darker. And then when you got to this switch off point, that's about right here. At the switch off point, they're actually equal pixels. And then the top row starts getting darker and the bottom row gets lighter. Okay, so you blur between, you take what was one row of pixel and turn it into two rows of pixels, where one row is getting dimmer while the other row is getting brighter. Okay, and another example, another picture of that was this one. Here's a picture that emphasizes the logical pixel versus the physical pixel. One way to think about this is, if you have a curve and it goes through a pixel, you basically, if the curve is on one side of the logical pixel, you don't see the logical pixels outside the curve, so you don't draw it. If the logical pixel is inside the curve, you do draw it. So this is a curved version of anti-aliasing. The ones we looked at before were line versions of them. There's actually two approaches, lines or curves. When you do curves, you actually look at it from the point of view of physical pixels, and you ask, is the physical pixel on the good side of the line, or is the physical pixel on the wrong side of the line? Any physical pixel on the good side of the line is the whole pixel's lighted up. Any pixel that's on the wrong side of the line, the whole pixel's dim. So this is what you wish you had. This is what you get. The person who drew this should have shown these logical pixels over here too. Yeah. So you're going to turn off that pixel, turn on that pixel, turn off that pixel, turn off that pixel, turn off that pixel, turn on that whole pixel there. So there's another way to think about it. Okay. And this is another, this is the same thing. If you've got curves, you want to know whether you're inside or is a logical pixel on the good side of the curve or the wrong side of the curve. If a logical pixel is on the wrong side of the curve, you turn off the physical pixel. If the logical pixel's on the right side of the curve, you turn on the physical pixel. So that's actually, there's 2 points of view of anti-aliasing. One point of view is this logical pixel point of view. Is the logical pixel on the right or wrong side of the curve? And what we're doing is this line point of view, where you're just going to take a line and you're just going to ask, as you go across the line, are you closer to, which pixel are you closer to? And weight the 2 pixels. Okay, we've hit the end of the time. Okay, now, I don't know what that was. Okay, so as I mentioned a minute ago, anti-aliasing is no longer all that important because it's not as important as it used to be, because pixels are getting smaller and smaller, so you don't see what's going on. You don't see the jaggies anywhere near like you did 10, 15 years ago. So I think in 10 more years, nobody's even going to worry about anti-aliasing algorithms. The pixels will be so small that the jaggies will be they'll essentially be invisible. They just won't be noticeable anymore. So we'll stop even worrying about anti-aliasing. Right now, 10 years ago, anti-aliasing was a huge part of computer graphics. Computer graphics books would have long chapters about anti-aliasing. And I think that's all going to kind of go away. On Thursday, we'll talk about color. And color is going to be another use of Lerp. We'll see a third time we want to use the Lerp formula. And this time, it'll be a very different idea, but it'll still be it'll be the same formula in a completely different context. From clipping to anti-aliasing to color, we'll keep using the Lerp formula. Okay, so we'll quit there, and on Thursday we'll do the color version of Lerp. And if you have any questions, send me email or go to office hours and let me know if you have any questions about the homework or about the review problems. Okay, so let me end things, and we'll meet again on Thursday. Bye.